Hello everyone, and welcome to today's webinar on full survey chemical analysis of plasma-resistant ceramic coatings. My name is Rena Samsu, marketing at EAG Laboratories, a Eurofins company. Before we get started, I'd like to go over a few housekeeping items for today's event. All attendees have been muted, however, we'd still love to hear from you during today's presentation. You will have the opportunity to submit text questions to today's presenter by typing your questions into the questions panel located in the bottom right of your screen. You may send in your questions at any time. Dr. Rajiv Soman, Director of Purity Survey, will be answering some of the questions during the presentation. We will also collect these questions and address them during the Q&A session at the end of today's presentation. At the end of the webinar, a survey will pop up on your screen. Your feedback is greatly appreciated and will help us to improve our future events. I would now like to introduce Dr. Xinwei Wang, Project Manager at EAG Laboratories.
Hello, everyone. Thank you for attending today's webinar. The topic today, obviously, you can see it involves full survey chemical analysis of plasma-resistant ceramic coatings. Here, you can see there's multiple concepts. Number one, we're interested in analyzing coatings, and that is not a polymer coating, it's actually ceramic coating. Number three is not only just ceramic coating, it is plasma-resistant ceramic coatings. So what we want to do with this, we want to do a chemical analysis, and in particular, full survey chemical analysis, meaning we would like to measuring all the elemental impurities in those ceramic coatings. So hopefully at the end of this one, we can address a couple of your concerns. Number one, what coatings we analyzing? Number two, why we analyze it? Number three, how do we analyze it? Number four, what information we acquire and what else we can do for it. Hello, everyone. My name is Xinwei Wang. Today's topic will be full survey chemical analysis of plasma-resistant ceramic coatings. As you can see, this topic will cover multiple concepts. Number one, it is for coating. Number two, it is for ceramic coatings. And number three is actually plasma-resistant ceramic coatings. And we want to do chemical analysis, particularly full survey chemical analysis, which means that we will cover all the element impurities in the periodic table for the source coatings. And in the end of this analysis topic, we hope to address a couple of questions you may have. Number one, what kind of ceramic coating we will analyze? Number two, why we analyze it? Number three, how do we analyze it? Number four, what information we acquire? And hopefully, what else we can do for you. Okay, my name is Xinwei Wang. I'm a manager for projects, and I have over 20 years experience in material science and engineering. I have over 10 years experience in purity analysis and the material characterization. Specifically, I'm specializing in solving purity-related industry troubleshooting or quality control using trace analysis techniques such as GDMS, solution and solid sampling-based ICP-OES-MS, IGA technique, TGIR, MS, etc. So today's topic will be covering a couple sections. Number one is we'll give a quick overview of EAG laboratory. Number two, we will go over plasma-resistant ceramic coatings, what is the sample characteristics look like, and what is the analytical requirement and the challenges. Then we will go over quickly of the principles of GDMS measurement as a tool for full survey chemical analysis. And then we will discuss specifically its application for plasma-resistant ceramic coating. And then we'll summarizing the strength and the challenges associated with this technique. So here you can see Eurofins EAG Material Science is a global scientific services company. It is established in 1978 with 16 laboratories and 5 business development locations in over 10 countries, and we serve more than 4,000 clients. We have over 600 highly educated employees combined with leading state-of-the-art technology equipment set enables us to leverage the power of science and engineering to accelerate innovations through creative problem solving, objective analysis, and expert interpretation of the data. We offer GDMS analysis in multiple locations. that um, including Syracuse, New York, France, and in Shanghai. Here is our EAG Smart Chart, which is an acrimony of spectroscopy and microscopy analytical resolution tool. It offers a concise visual reference tool for comparing analytical techniques, permitting one to compare detection limits and the analytical resolutions for numerous materials characterization in techniques, evaluation of the surface, purity survey, and imaging services as well. So each bubble or bar represents a different analysis tool, and surface analysis technique are represented inside the box. The box techniques are represented outside the box to the left, and to the right, to the bottom there, those are imaging tools, and those detection limits are shown on the right and the left axials. In this webinar, we will focus on GDMS analysis tool. The technique can provide full quantitative survey analysis of trace impurity in bulk materials. On top of it, it can also provide depth-specific distribution information of impurity in engineering coatings and thin films. For more techniques, you can refer to this website link. Okay, the purity surveys in Eurofins EAG is feature multiple group of techniques. Number one group of technique we have is purity analysis, which is covering both solid sampling technique like GDMS. We have 25 plus instrument in-house, which give us the analytical redundancy and ensure uninterrupted services to the industry partners. And we have a solution technique such as ICP-MS, and we have 7 of them. Again, it is designed so we can provide uninterrupted services. And we have both solution and the solid sampling ETV ICP-OES technique and IGA technique, which covers gas forming elements such as hydrogen, carbon, sulfur, nitrogen, oxygens. And on top of the purity analysis, we have thermal and microsampling analysis technique as a supporting technique to those mainstream technique. We have thermal analysis such as TJIR-MS that is dealt with focus on the outer gassing in flow gas conditions. We have deep mass focusing on outer gassing in vacuum conditions. And then we have laser ablation ICP-MS and the LIPS that are focused on microsampling analysis. And then we have RGA, EGA dealing with moisture and other inner gas, outer gassing from hermetic devices, particularly on the medical and electronic devices where the reliability is often impacted by the outer gassing species. And on top of that, we also have suction analysis that are just a supporting technique for characterizing surface area as well as pore size distributions. Specifically, our main analytical capability is glow discharge mass spec. You can see we have multiple generation of instrument, including the early generation VG9000 to new Astrum, which is replacement of VG9000. We also have fast flow based element GD technique, which both operates on the continuous mode as well as in the pulse mode. So our GDMS technique is designed to drive technology innovation and redefine high purity analysis. We have all the commercial instrument models from VG9000, as we mentioned earlier, which is the earliest generation. 2 is replacement, the new Astrum. We also have fast flow GDMS, and these which both operating in the continuous mode as well as pulse mode to address different issues. So first we will talk about the sample characteristic and analytical requirements for ceramic coatings. For plasma resistant ceramic coatings, why would we need it? Well, in the semiconductor industry, they have a etching process which uses CF4 and oxygen plasma. And those plasma will generate ions, radicals, which can aggressively attack the chamber wall and forming particles and volatile metal fluorides or any other oxides or cell nitrides that can subsequently contaminate wafers. As such, plasma-resistant ceramic coating are commonly used to protect the chamber walls. Give you an example, if we wanted to develop ceramic coatings that have a fluoride resistance, then we need to look into those fluorides, corresponding fluorides, which have the highest boiling point. You know, whether you have a high boiling point, it's less likely they're gonna fall off from the wall. So here is a couple of candidates. You can see aluminum, yttrium, erbium, zirconium, and other rare earth elements. Their corresponding fluoride has very high boiling point. As such, they are ideal candidate materials for plasma-resistant coatings. On the other side, those will forming low boiling point elements like arsenic, chrome, and other transition metals. They need to be very carefully controlled so that you have a clean process or contamination-free manufacturing process. In that sense, you do need to have a full survey capability to check out all the impurity, not just those listed here, so that it can have the necessary quality as a plasma-resistant coatings for semiconductor applications. Here, give you a typical example of what the ceramic coating look like. Here is a top view as well as a cross-section view. You can see those samples. They are typically their composition as those aluminum, yttrium, rare earth oxides, fluorides, or oxyfluorides. And you can also see the surface is very rough because they are made by generally can be by a spray plasma process, and so you have those molten liquids droplets is rapidly solidified on the substrate and give those features, which has tens of microns in length scales, and it has thickness up to hundreds of microns. And because this process of making it is either from the raw material or the processing equipment as well as processing conditions, the contamination is unpredictable. So as such, you can see there is quite a bit of analytical challenge, and how do we address that? Because it's plasma resistant, then generally means also chemical resistance. So solution technique is generally not very viable, and because it's a ceramic, and it is generally not electrical conductive. So if we are going to using ion beam sputtering technique, then we need to use secondary electrode to assist the sputtering process. And because those materials are generally advanced and they're new, and reference material are not easily available, this calls for techniques that with very limited matrix effect. Otherwise, the precision accuracy cannot be attained or necessary to satisfy the industry needs. And as we said, because the contamination is generally unpredictable, so it is desirable to have elemental survey capability at high sensitivity. So here we wanted to go over quickly all the GDMS fundamentals. For details of the GDMS technique, you can check out our GDMS webinar for more details as shown here. For any technique, we have to deal with two things or many measurement. It requires deal with the precision. It requires deal with accuracy. The precision is how well the measurement repeats itself, and accuracy means that how far off the measured value is from the true value. There are four scenarios we're dealing with. The first scenario is it neither has accuracy nor the precision. And quite frequently, you may also see a situation where you have a good average accuracy, but are not precise. And often we are dealing with a scenario where you have good precision, but not accurate. Our ultimate goal is to have both precision and accuracy. So we will talk about those, how the accurate GDMS can be used to achieve the necessary precision and accuracy. GDMS as like any technique, direct solid sampling technique are ideal for trace analysis of the solids because number one, they are easy sample preparation. So it means that number two, it has low contamination risk because you are not is a direct solid sampling. So you eliminate many steps for the sample preparation. And number three, because dilution is limited, so it has very high sensitivities. And but there is one major impact that needs to be dealt with. It is a matrix effect. For any solid sampling technique, this matrix effect has to be addressed. They may be in a different way to affect the measurement uncertainties. Give you example is that we have a conductive solid samples, and we can use primary ion beams to sputter sample and collect the secondary ions. This is called a secondary ion mass spec. You can see this technique will have a very strong matrix effect because the ion actually directly generated from the sample itself. So it will be the relative ion yield will be dependent on the matrix. In EAG, we have thousands standards to make the same quantification possible. Second technique is called sputter neutral mass spec, which are collecting both the secondary ion signal as well as some of the neutral neutrals, which is further ionized by auxiliary ion beam. You can see, notice that there will be some multi-state matrix effect. Part of the reason is that there is an atomization ionization separation process because of sputter neutrals. So what if we can maximize this process, or we suppress the secondary ion generation, then and boost the neutral yield? Here we go. We have the glow discharge mass spec, and this is using argon ion beams to sputter sample and suppress the secondary ion yield by biased voltage, and boosts the atoms, sputter atom yield, and these atoms are then diffused into plasma where it is ionized to analyte ions, which is subsequently analyzed. This atomization and ionization separation process in both time and space minimize the matrix effects, which made GDMS is one of the ideal tools for full survey chemical analysis for solid samples. So here is how actually the principle, how it works. In the GD ion source, an electric field is established between the anode and the cathode sample. This voltage drop is about 800 to 1000 volts, and the spread of small argon amount of argon is then introduced into the GD chamber, forming stable plasma instantaneously in the electric field. And those ionizing species then will be accelerated in the electric field toward the cathode sample, and they transfer the kinetic energy to the sample, causing their sputtering. Okay, and those sputter neutrals will go through the pending ionization process predominantly, and then be extracted out to the mass analyzer for analysis. Couple of things you can see that the sample is atomized in the glow discharge uniformly, layer by layer. Number two, the sputter species, predominantly neutral atoms, they are diffusing into the plasma and are subsequently analyzed. This actually causing that you can clearly see there is a separation of atomization process and the ionization process. Number three is that the ionization process is not by electron transfer, is not by charge transfer, not dominated by charge transfer or electron impact, but rather it is by the pending ionization process, which is non-element specific. This means that you can generate this GD source can generate a stable ion source with a minimum influence from the sample property, such as ionization potential, electric conductivity, etc. This serves the basis for the quantification. One of the important aspects for trace analysis is that during the plasma sputtering process, you will generate a lot of polyatomic interference or isobar interference. So the ability to separate or resolve those mass interference is a key for accurate trace analysis. Give you an example here. If we wanted to analyze in the irons, iron impurity in the silicon, you will see there's multiple interference happens. To the iron 56, you have the silicon diatom, and you have argon 40, oxygen 16. You can see they have very similar masses. If we were using quadruple mass spec, you will not be resolve those separate differences. However, if we have high resolution mass spec, you can clearly resolve them if we have the mass resolution over 2500. So we can clearly resolve those differences, and then it give us the ability to accurately and reliably measuring the multi-element. Instrument-wise, this is an example of how VGG 9000 GDMS model looks like. It has a GD ion source, which is serving, is mounted on liquid nitrogen, cooled by liquid nitrogen, and it serves as a stable ion source. And those once ion is generated, of course, it goes different directions, and you have different kinetic energy and mass charge ratios. So you need to, number one, extract ions and reshape it through the ion lens, and then go through multiple lens filters, such as magnet and electrostatic magnet analyzers to double focusing. in the magnetic and electric field. So in the end, you have ions of same mass charge ratios and same kinetic energy hitting the detectors. We have two detectors. One is photomultiplier and the Friday, which covers different concentration range, and it has automatic switching capability, depends on the concentration. With this design and geometry, it allows us to do the analysis. GDMS is able to handle versatile sample forms of solids, including powders, ingots. The sampling process utilizes pin or flat cell geometry. If it's a pin, it is 2 by 2 by 20 millimeter. And if it's flat cell, we want ideally at least the sample size 10 by 10. And for ceramic coupons, we ideally want actually this size with a metallic substrate of a few millimeters thick. So we talk about sampling diversities and the requirement. So how it does the quantification. In GDMS, you see is a MS, so it is looking for the ion current. So another thing is GDMS essentially is an internal standardization method. So what it uses is looking for the ratios of ion current of analyte of interest to the ion current of a matrix element. That from here you can see it is required the matrix composition is consistent and uniform. And with this one, it will give you ion beam ratio, but this ion beam ratio is not it's a concentration yet. So we need to know that the relative ion yield of the analyte as matrix. So what you do, you have a relative sensitivity factor, which is factoring the relative ion yield of the analyte X in that particular matrix. So from this one, you will have the concentration. And this ISF set has multiple features or characteristics. Number one, it is constant over a wide concentration range. And number two, it has limited variation with the matrix composition. This has been studied and concluded from multiple literature studies in early time. The reason for that is actually going back to the GDMS measurement principles, is that it's a separation of atomization process and the ionization process and the infinite dilution of the analyte X in the plasma. So, and then the penionization, which is a non-elemental specific process. So all those together, it builds into this ISF set that it is pretty constant over wide concentration range, and it has limited matrix effects. Give you example is actually, this is our generalized ISF set. You can see if we assume iron's ISF set is 1, you can see most elements, more than 50 elements, the ISF is around 0.5 to 2, and then a couple extra is between 2 to 4. So this is because of this, a strict matrix matching is generally not required for quantification. And a generalized ISF can be used by measuring single multi-element standard sample to establish it. And those are, as a result of this, you see the ASTM methods and the literature is being established for those to support this observation. So before we jump into others, I wanted to focus on the reporting limits, specifically because we are dealing with GDMS, which is a technique with a limited matrix effects. So now all the reports we give is actually showing the reporting limits or actual values. The reporting limit is the lowest concentration or mass fraction value that we are reporting in our analytical GDMS reports. The reporting limit is understood as the lowest concentration at which analyte can be detected in the sample, and its concentration can be reported with a reasonable degree of accuracy and precision. So what is this reasonable accuracy, degree of accuracy precision? We have criteria which states that if it means that there is accuracy within 20% or precision-wise is within 20% RSD for repeated measurements. And from here you can see this is a mass detection limit, and this is an analyzed signal that can be quantified. And in our case, we actually using the most conservative way to reporting the value. So it is reporting limits. It generally is higher than the mass detection limit as well as limit of quantification. So EAG developed its own proprietary software to help analyzing the data. There's several important features of this software user interface you can see here. Number one, we establish traceability of any So to know who is doing the analysis. Number two, you can see this user face is capable of handling data from all the three type of GDMS instrument we have, including the VG9000, New Astrum, and Element GD. And we have built-in mass interference calculation. And if the analysis is tied to ASTM protocol, it will be automatically show up and link to the protocol for quantification. Here is a GDMS analytic feature, a summary that pertinent to impurity analysis of ceramic coatings. You can see we using the in terms of glow discharge source is done on the reduced pressure mode, which require cooling. This is both VG9000, New Astrum is capable of doing that. The sampling volume wise, it is 8 millimeter diameter plus 10s times by 10s of micron depths. So indium mask will be cover a small fraction of the sampling area. This indium mask is used as a secondary electrode. And it has mass resolution from 400 to 4000, which is capable of resolving most of mass interference. And it has an elemental coverage of virtually the entire periodic table. For non-metallic impurities such as carbon, oxygen, nitrogen, it is possible under special conditions because you have to lower the background. And it has limited detection limits in the submicron, microgram per gram or sub ppm levels. Wanted to point out that the lower detection limits or reporting limits is possible based on the special request. We can optimize testing parameters such as the mass resolution as well as the integration time or cell. Those parameters adjustment or optimization process. Its quantification is based on ion beam ratios and non-specific ISF values. And it has pretty broad dynamic concentration range for detection of trace and outer trace elements. And mostly the information are bulk, but it's possible for contamination, surface contamination type of things. We're using proprietary software to check the mass interference, calculation, the traceability, and automatic links to ASTM protocols. So now we wanted to talk about specifically the case studies of survey analysis plasma resistant ceramic coatings. Here is a typical plasma resistant ceramic coating look like. The surface morphology looks like you can see is pretty rough. And so we were using an indium mask that with a diameter of about 8 millimeter. Those black dark lines is indium from the indium mask. And this is actually the sputtering crater after the GDMS sputtering. You can see you have depths from about 25 microns. So it tells you that it does sputter very well and it has inadequate depths. So here is actually the parameter we're using. We're using both GDMS instrument, VG9000 or New Astrum. And the representative sampling volume is 8 millimeter in diameter and 20 to 30 micron in depth. And it has full elemental coverage with the detection limits in the submicron to ppm levels. Okay. So the first thing for any method development or validation is you look at the signal or the matrix signal. Can we actually spot it, successfully spot it? Number one. Number two, if it does spot it, what's the signal stability? Number three is how strong the signals, because those will establish what's the precision look like, or what's your sensitivity look like, or your reporting limits will be look like. Take example, if we have yttrium, pure yttrium coatings. Here is a signal of the yttrium, the red line, and the oxygen is blue line, and the indium as a secondary electrode. You can see the signal is very stable, and the actually is below 10%, which is similar to the metals. And similarly, you can see for yttrium stabilized zirconium or the yttrium aluminum garnet, the yttrium fluoride, we can all achieve stable sputtering with very high signal sensitivity, signal intensity. You can see most of the signals, matrix signals, are in the 1E9 levels. So that gives us the ability for high sensitivity detection. And this signal stability gives us the necessary, will help us to establish the precisions. So as we said, mass interference is a big deal for any trace analysis. Here we want to demonstrate to you how actually our GDMS instrument is capable of resolving those mass interference. Give example is that trace level of iron in the yttrium stabilized zirconium target. You can see iron 56 is here. We can clearly unequivocally to resolve the interference from argon 40 to oxygen 16 and other interferences. So because of that, it gives us the ability to accurately, precisely determine the iron levels. Similarly, you can see we can do the chrome. Chrome has even more interference. This is chrome 52 we use, and you can see it can easily resolve the interference from argon 40, carbon 12. Or argon 36 and oxygen 16. So because of this high resolution, high mass resolution, it is possible to unequivocally to determine those trace transition metal impurities. And before any for any method development or validation process, we need to establish precisions. And to establish precision, we need to evaluate the actual reference material, how homogeneous they are. Here we using this. This is a reference material we work on, which is 8% yttrium stabilized zirconia is from Jalaska, and we're using the technique called the laser-induced breakdown spectroscopy to evaluate the composition homogeneity. And basically, you have a laser beam scanning through this one, and you have multiple scans, and you monitor the yttrium, zirconium, and oxygen content changes through the landscape through those in those scanning directions. This scanning direction is length scale is 20 millimeter by 1.2 millimeter. We have multiple scan, and you can, and then the yttrium, zirconium, oxygen distribution patterns is mapped here. You can see the yttrium concentration varies from 14.4 to 14.04 with ISD about 3%. Okay, similar is observed for zirconium and oxygen. So this gives us the confidence that this is a fairly homogeneous reference material that we can use to establish the precisions of the method. So here we did a precision measurement of this standard. As you can see, the couple things I want to talk about. Number one is the elemental coverage. Here is a partial of the elemental list that we covered, and because those are actually most of that detectable. If it's not detectable, then it's difficult to establish the precision. You can see from boron, sodium, magnesium, and most of the transition metal, and a couple of refractory metals are shown here. Number one. Number two, you see we have really low reporting limits from typically 0.5 or even lower or so. And those are the replicas we measured in separate days, and this gives you the ISD. You can see at the ppm level, those elements, the precision is 10, 20, or 30% or so. Some of the elements are even higher, has higher, but I will show you for plasma of ceramic coatings, this is not unusual. One of the reasons is that in the plasma ceramic coatings, that impurities are often come in as inclusions. So here I give you example. We're using SEM EDS to look into the surface. If we see those inclusions, which is actually aluminum oxide. So if you hit it, you have it. Otherwise, it is not there. So samples heterogeneity often is one of the major source for contributing to the measurement variations, or the major source to lower the precision. And here, we want to show you the typical reporting limits for the ceramic coatings we do. Again, this is only shows part of the elemental list for illustrative purpose. It is possible to do full survey elemental analysis. Number two, you can see the detection limits are generally 0.05 to 0.1, which is can satisfy most industry needs. We want to point out that the lower reporting limits is possible by, as I said, by optimizing the analytical parameters, such as extending the integration time, lower the resolution without a compromise mass interference issues, and boosts the signal intensity, the matrix signal intensity. So GDMS is not only used by demonstrated to those ceramic coating we demonstrated earlier, yttrium aluminum garnet, or yttrium stabilized zirconium, or yttrium fluoride. But these are actually used in widely many other plasma resistance coatings. And those are, for example, they can be rare earth oxides of those yttrium aluminum or rare earth or the fluorides, and those typically have aluminum alloys or stainless steel substrate. And those are the critical impurities you can analyzing. Basically, the full survey chemical analysis. Okay, and then the second type is on the silicon carbide, titanium carbide, zirconium carbide, tantalum carbide, or boron nitride. So that are with a graphite substrate. We also do those routinely. Again, the impurities, those impurities can be easily measured. And I want to emphasize not only those are impurity, but pretty much the entire periodic table can be analyzed. And then there are also other substrates like silicon carbide and silicon, as you know, those silicon carbide are deposited on that. So overall, we are not only using it for the rare earth oxides or fluorides or oxyfluorides, but I also use it to analyzing the pyritic carbon, silicon carbide, all those coatings. So it's being, we're analyzing a couple thousand samples a year to support the industry. Here is a summary. GDMS strength and its limitation. Number one, GDMS is really a full survey tools. It can cover measuring 72 elements, most of the stable isotopes of those elements. It can acquire depth-specific distribution information. But it can also just focus on the bulk analysis as well as the surface contaminants. It has excellent long-term precision as a solid sampling tool, which really lower the contamination risk due by the sample preparation. It can achieve possible billion or sub-ppm level detection limits. It has limited matrix effects. This is one of the main features that it allows us to do the semi-quantitative to full quantitative analysis if standards are available. Obviously, it's a very robust technique because it is a direct solid sampling technique. So, like every other technique, GDMS has its limitation. It is very important the sample is homogeneous because it's based on ion beam ratio quantification. So, and you rely on the uniformity of the matrix elements. And number two, obviously, because this technique is done on the reduced pressure, so the sample needs to be vacuum stable. Complex matrix structure which contain organic liquids obviously is not very effective on those without doing some special sample preparation. And typically, but for those, we have other techniques available in-house, such as solution-based ICP, OES, and MS. It doesn't have the capability to do laser resolution, but we have other tools. We have laser ablation, ICP-MS, as well as LIPS that can do micro sampling, as I demonstrated here. LIPS is being used for the homogeneity evaluation of the reference materials. For atmospheric hydrogen elements like hydrogen, carbon, oxygen, nitrogen, there are other tools we can use, and we typically using the IG technique. But there's other techniques can be used as well. So overall, GDMS is being a very successful story in the commercial world for the testing and qualifying many metals and alloys. There's multiple testing standards, ASTM methods, and there are more we are developing. And generally has been an integral part of high purity materials manufacturing, trading, supply chain, QC, QAs in the special alloys for aerospace, sputtering targets, high purity metal powders, ceramics, and specialty coatings, opticals, implants. We're not stopping here. Why choosing EAG? There are a couple of things we do here for a reason here. We treat clients confidentially is our part of our core for the business. We establish thought leaders in investigative science. We have extensive knowledge base and skilled expertise. In terms, we often take a multidisciplinary approach to support you. For example, this ceramic coatings, we not only do the full survey chemical analysis, but actually we do a grain structure and a grain orientation analysis with EBSD. We can do cross-section, and we're using XRD to look at crystalline structures, and using LIPS to evaluate its through the composition homogeneity through the coatings or laterals or can also use laser ablation ICP-MS as well. So you see, we're often not limited to one technique, but actually a multidisciplinary approach to support your product development or QC/QA process. We have a lot of instruments. As you can see, we have 25 GDMS, so we can easily scale with your demand and meet your time constraints. We have more than 25 instruments, all kinds worldwide, to support all kinds of needs. We are a global leader for material testing services. And of course, we have the necessary accreditation, ISO 911 and ISO 17025, which is necessary for the third-party testing labs.